Gaussian 16?
Oh, that would be nice.
They haven't.
Well, Corey's down for
Did you look at the new features of Gaussian 16 at all? Did you look at the new features of Gaussian 16?
I'm only gonna look.
I glanced through, but it didn't impress to the death.
I'm only gonna look at my boss or someone at the SU page to have the license.
Why? You use a nurse
Yeah,
if you benefit from it.
I guess yeah. That would.
I don't know if you, I don't know the features.
So, who we are and what we are doing here? What are our goals?
To figure out Fermi golden rule.
But why we need Fermi golden rule? It depends who we are. If we are veterinarians, then we probably do not need it. Why do we need it? Suppose that the grade is guaranteed for the class. Do you still need it? Do we need it for our career or for curiosity?
Yeah.
So what it is and why do we need it?
I don't know what it is.
Fermi's golden rule
Yes.
gives us a way of predicting the likelihood of a transition, right?
Yes. Yes.
It can also help with overlap of molecular orbitals.
That's how it predicts the likelihood.
That's what you need.
But
Not bad.
So there is a little paradox. When we played toys in the lab, I mean mathematical toys, or programming toys, you have seen that the occupation of the originally unoccupied level grows quadratically at the initial time steps. Then Levi suggested that why don't we do normalization? Or you don't need normalization, you can just subtract from the originally occupied level populations of all unoccupied. And then we'll get its trajectory, its occupation as a function of time, right? Make sense? And then we will see that it depletes quadratically. 1 minus constant times t squared. Right? So as time passes by, more and more probability is withdrawn from the originally populated level. More and more quadratically. Now, it looks like you two are already exposed to Fermi golden rule. What would be the depletion law as function of time if we believe in Fermi's golden rule?
depends on the wave function of each state, how well they overlap.
But suppose that we know the overlap. It's constants that are given to us. And you've told that it is a rate of transition. Rate means what? First derivative. It means that at short times it will be linear. Correct? So from what we did in the lab, we see that the probabilities change with time quadratically at short time. And this golden rule, which means that someone values it a lot, gives linear change of probability with time. I think it is enough of a challenge to speak about it a little bit. What is the answer? Why? In which cases our finding from the lab will violate? We will cover material of today's meeting in like 2 minutes right now, and then the rest will be technicalities. So let's guess when it will violate.
Long time.
One option, other options. You probably are thinking about that you have more channels or longer channel to withdraw the stuff. Yes. So one option is longer time, but we know that it will be oscillations. Well, other ideas. No, see, here's a true paradox. I want to catch you on this. So if the change of probability of the occupation probability with time is quadratic, then in the limit t equals 0, the slope is 0. So there will be no change. And in Fermi's golden rule, it is linear change. So even at the very short time, it doesn't work. So long time, short time, any ideas?
Time.
Let's think out of the box. Let me remind what we are doing to Sam. So in the past, we considered time-dependent perturbation theory that gives solution how the occupation of levels change with time. And we saw that not wave function, but wave function square, population of orbital, changes as quadratically with time. If it was unoccupied, it grows like constant times t square. If it was occupied, it is 1 minus constant times t square, right? And there is a famous piece of knowledge, Fermi's golden rule, that gives the rate of transition from somewhere to somewhere. Rate means it is a first derivative. It means that it is linear in time. So what did we miss? Why we derived everything so carefully and we got results that coincide with exact solution? And this, we do not know who, Fermi, tells us otherwise.
We're gonna do a delta E, energy level between the two states.
Good direction of thinking.
So that's wrong.
No, it is not wrong. It's just asymptotically approaching the right.
I see.
Which system did we apply our methodology in the lab?
Spin.
How many levels?
2.
Fermi's golden rule? Is he limited to 2 levels?
I thought yes, but maybe not.
No.
Oh.
Some overall?
Oh.
Well,
Final states.
yeah.
So, in what we did before, just for simplicity, to get the grasp on concepts, we considered one initial, one final, 2 states, 2 level system. And if we consider continuum of final states, infinite number that are densely spaced, like bulk, then there will be a little transition to one, to another, and when we integrate constructively all possible transitions, then the net total change of probability is expected to be linear rather than quadratic. Make sense? Well, you do not need to believe this. We need to prove it. So this was the motivation goal for what we are going to do today. A little of administrative things. Let's. Do you have finals or whatever? Not finals. Midterms before the spring break. You do? You don't?
I have 2 of them.
Oh. So
One on Thursday, one on Friday.
only 2 busy people. The rest are more free. So let's entertain homeworks and presentations. The estimated time for the homework is 20 minutes. Estimated time to prepare a presentation, like a minute per slide.
So it takes as long to prepare the slide as it does to talk about the slide.
Well, I just want to encourage you. Maybe it's a little longer. So, here's what we did in the web. And the copies went through the emails. So, let's run the code that we collectively developed in the lab 100 times more, and So it's a lot of writing, but it is basically a summary of the context of what we were doing in lab, and there is a verbalization of a question that we discussed all together. What is the precision of the perturbation theory as the function of the offset between frequency of perturbing oscillation and the energy offset and the of the levels? So you can just run the script, plot the figure, and add a couple of sentences of the comment. So it is expected to be really simple. Any questions about this? Yes? No? Make sense? Good. Whew. I'm just waiting. Okay? Yep. No objections?
If not, you get an email, so. If not, you get an email.
Sounds dangerous. Well, Brandon told, yes, no problem, easy. And you know, maybe.
I guess I just have to take more time to formulate.
Fair enough. It took me much longer to write this rather than we spent in programming and running.
Why isn't the inner product? I mean the dyadic product.
Because I was lazy to type matrix as an equation in equation style. It's just replacement of matrix form. Okay.
So this is the homework that you gave us yesterday.
Yes, it's just formally formulated in a verbal form.
Yeah, yesterday was verbal. This is written.
Yesterday and today were verbal, but yesterday were oral verbal, and today is written verbal. So, how are you looking on presentations as a replacement for like exams and midterms? Are you still staying more or less enthusiastic?
Yes.
Good. It is what I want to hear. So let's practice again. Well, our original type of democracy. You've told that it doesn't fall into exact definitions of democracy.
Okay.
So here is the list of options to present, and let's leave one copy with each of you for the memories, and one copy with where you mark your preferences. You can mark more than one, and I will collect it by the end of the meeting. Whew. I do not have more excuses to postpone derivations by the blackboard. So presentations March 9th, March 7th, and on the International Women's Day we will have lab.
International what day?
Women's Day.
Oh, it's March 8th? Oh, I didn't know that was a thing.
Well, in some countries it is more celebrating and some less. It's like another reason to.
Not have class?
Well, if there are girls in the class, then as a gift you can cancel the class.
We need to get a woman to join us for that day.
So we have already done this motivation. So we do have solution for first order correction. Which was something like minus I, the matrix element plus and here with a long result of integration. Right. So we explored this solution in case when it is applied to our system, when our n equals 1, k equals 2, and there are no other indices. So we look for originally occupied ground state, and we look for probability how the excited state is populated this time. Now let's inspect if we can apply the same theory to the case when we have one initial and a lot of final states. So we irradiate the system again with the light of given frequency, and then it will be in resonance with one of the levels, and with others it will be a little more and more off resonance. And our goal excited is growing, and E ground is quadratically decreasing. So let's look on the P ground as function of T. So how quickly the occupation of ground state will be depleted, how quickly the population is getting transferred from ground to either one of the excited. So let's put something indefinite. So how would it look like? Will it be quadratic or linear? Start with 1. This function of T. And we will be looking for the rate. So our main observable for today that we are chasing will be rate of this depletion. So basically we will take the slope at time t approaches 0 and see how does it depend on the parameters of this perturbative solution. What we place in the Hamiltonian, what we see in this first order solution. So our goal is to, or technical goal, is to get P ground as function of time. And then look for the rate as dp ground time dt. Right? And then we will be able to tell that at small time p ground of t approximately equals 1 minus rate times t. So when we get this rate, this will be our Fermi's goal model, not our. When I opened Wikipedia, it tells like everyone calls it Fermi golden rule, but it was derived by Dirac. So what is our plan? We probably may want to subtract, since we assume that it is one particle quantum mechanics, everything is normalized to one, then we just subtract occupations of all remaining orbitals, right? And if you would do it for just one orbital, for single orbital, you would get 1 minus some constants times t squared. And the rate will be rate in the limit t equals 0, it will be 0. But here we expect something different. So we just need to perform this summation. So if you take square of this, round to state n, execute. Then we need to take the square of take this function conjugate to itself and then perform the summation. interesting things are done here. Now we should call an emergency mathematician or call for a mathematician inside us. So I'm going to take this function conjugate and without conjugation. Which means we swap, we assign here I'm just trying to find the excuse for not doing it.
We get 2 terms that cancel. Sort of.
Let's try.
You these,
But it is multiplication.
right? And then these add, so that'll go to 0. So you,
No, but you also have the -1.
yeah, that's.
So you do a
So that
foil
adds-
within foil.
Right? So it'll be
Because-
1 minus.
So when these are multiplied here, you get 1 term minus 1 term times 1 term. So then that you back to
We'd foil first, right?
Yeah, you foil first, but then
within the foiling.
first
Front,
outer
inside, outside,
first.
last.
First, outer, inner, last.
First order, and then what is you?
So
Foil.
first, outer, inner, last.
First outer, inner, last.
He's
So-
only doing first versus. He's only doing 2.
So if you have.
He's not doing the whole bracket.
So that was just this one, this one.
Yeah.
Okay.
First, outer, inner, last.
And you call it foil.
Oh, front, inside, outside, last.
No, thank you. I'm mistaken.
Front is
First.
Okay,
No, it's first.
thank you. Thank you.
front.
We keep going, or?
No. I have an idea of how we can simplify our life. Not drastically, but a little bit.
It's a negative cosine.
Yes. What if we... Let's discuss, can we make our life simpler if we consider this term as t divided by 2 and q minus omega capital times e by t minus omega divided by 2
Outside, last.
if you consider 1 as a product of half argument forward, half argument backwards, and here we just split, factorize this term as half argument forward once, half argument forward second. And then this will be times 2 cosine no, if it is minus, it will be sine. Then we'll get sine here, or we'll get sine functions everywhere, and maybe we can factorize them, and we these terms will cancel eventually. What do you think?
Isn't it 2? In the 2 times, not divided by 2.
No, but it's, oh,
In the brackets, it's 2 times, not divided by 2. But then you got,
Divide by 2, divide by 2. Here
okay, so when you multiply out, you get e to the it divided by 4 omega minus omega minus 1.
no, you add them. The exponents add.
Yeah. Oh, that's right. That's right.
So then it would just be,
Right, right. Yeah, no, that's right. That's right. I was
I have the
it's right, it's right.
I have the even better plan, not for rigor, but for keeping time. Let's take only the first term and process it.
no, but the first term, you still need to have multiplication. You can't do 1 minus the e minus e plus 1. It's still,
Should be something like this.
right?
Or
No, I filed it out.
I think he already.
But then you should only get 1 1, not 2 1s if you FOIL it.
I think it's do -1 times -1.
Yeah, but
So-
then you only get 1 1, and all the other terms have e in it.
No, not the first one. Those canceled. We needed 0.
Oh,
Last time we considered that we are getting non-zero solutions only if we are close to resonance. And now we will be considering only levels that are not too far offset with positive frequency. So probably we can drop these two. And then this term will be sine with exponential accumulating phase with plus, and if we process this term in the same way, we will get we can process it as e minus I over 2 t times delta times e minus I over 2 t minus of k minus omega capital times t divided by 2. One star. Well, star is bad. It's one diamond double tap. Make sense? So if you assume that we are not far from resonance, then we can drop second term in each factor, and then the first factor is oscillating exponential times sine, and second one is exponential oscillating in a different directions time times sine. And the sine function is the same, with the same argument for both terms.
Is there an overall negative sign? And the second term? E to the minus I minus e to the I.
Let's double check.
In the first term it's e to the I minus e to the negative I. And in the second one it's e to the negative.
Come on, here.
Well, this is
If you don't talk, he doesn't make you go to the void.
right. The I x minus e to the negative I x equals 2I sine x over 2. Just x. Right.
Yes. And sine of minus x is equal to sine x.
Oh, okay.
Good?
That's right.
So Diane was concerned here, if we swap the signs, it means we get sine of minus x.
Minus sine of x.
Right? Yes?
Minus.
Minus sine of x.
So then if we keep the same argument as here, then we need to put here minus sign. Yes? We can put, I think the final result will change. Now we are multiplying these two factors. So here we do have the same factor but with opposite sign, so we can cancel it. Then we do have 2 times 2, 4, I times I will be -1, and the -1 due to careful I of data times sine square of omega k minus capital divided by 2. So -1 times -1, 1. And then this term will go into here, into our summation for our so. So this one is full.
So now if you hear that from any other kids, you know what it means.
So we're looking for occupation of ground and summation. And if you want to keep the arguments of sine in the denominator the same, you can divide it by 2 here and multiply by 4 outside. What is this?
Dots, density of states.
Yes. Density of which states?
Unoccupied.
Yes. So basically, what we are going to get at the end, I have something interesting to tell. Very related to the class, and not as boring as derivations. We are going to get the equation that we use when we declare how we compute absorption spectrum. Right? And in case they all have the same, so this one is oscillator strength. This is delta function at the difference of energies. And if they all would have the same oscillator strength, then it would be summation of delta functions of which will be density of excited states. So summation of delta functions at energy difference is density of states. Just how many states are per energy in them. Right? Can we apply the same concept in evaluating this expression? we know that summation is equivalent to integration times density of states. So if there are so many states per interval, then we can multiply the function times number of states, and it will be equivalent to summation. So we are going from summation to integration. And I'm going to erase this entertaining records and keep going with the new records. So now letter K is a continuous index of all states. We have them continuously distributed. Then we have number of states per energy interval, and then we write the same things that we had before. Matrix element from the ground to state K times strength of field. So same expression. With element of these two states. But now we need to make one more replacement. We need to see how the excitation, transition energy for individual excitation, we also need to make it continuously changing. So when we do this integration, it means that the offset is changing continuously. And to simplify the life and avoid designing a conversion from index to the energy offset, why don't we select the energy offset as the variable of integration? So now we will count our states based on their offset from the frequency of the perturbation. Set is selected as variable and for integration. I think this was almost the last intellectual, scientific input. The rest will be pure math. When we were making an exercise yesterday in the lab, and when we were here 2 days ago in the class, we were considering spectroscopic experiment, where we have energy offset fixed because there are two levels, and then we continuously change the frequency of the incident light, of the perturbation. And we were checking whether it is in resonance or off resonance. And some of you, I think, asked like, what if we fix the frequency of incident light, like using laser with fixed frequency, and then apply it to different transition energies, right? Today is your day. So we assume that the frequency is fixed, and it can affect levels of different energies, or different transition energies from the ground state. For simplicity, we will assume that transition dipoles are the same for each transition. Otherwise, it will be just too much to do at once. So we put them out of brackets. So how can we simplify it even more before we get to all mathematicians inside us? I suggest we assume that these transition dipoles are the same for each transition, and if we are staying in a very narrow vicinity, then we can assume that density is homogeneous. We can place it out of the integration. The only thing that we will need to integrate is this function. You may disagree. It is a strong approximation, and one needs to justify it. So what I suggest to do is to place is the density of state outside, which we need to justify. Well, if we take this function and plot it at different times, and we chase the longer values of time, then we will see an interesting trend. So what I'm doing here, this I'm justifying placing density of state outside of the interval. And the reason for doing so is analysis of this function, of this blue function. So for small t, very near 0, this blue function will look this way, as you may have seen in MATLAB simulations. If we redo this, so if you recalculate this function at larger t, then it will repeat the same qualitative pattern, but it will be taller and narrower. So as far as time goes by, the function becomes narrower and narrower. And in the limit of long time, it is a good approximation for delta function. So basically, it will pick the values of the density of states only near the resonance. So this is a justification to place density of state outside of the interval. So blue function, this sinusoidal over quality denominator. Blue function approaches delta, Dirac delta, and picks values near resonance. Because of this reason, we place density of states out of integral. So qualitatively, we will have to integrate this function, which is very close to delta function. And we already expect that integral of delta function equals what? Huh? How many?
The value of the
Yeah.
function.
Huh?
The value of the function.
Delta, just delta.
Oh,
Integral delta minus infinity to infinity x dx. 1, right? If it is a good normalized wave function. The only question that we ask ourselves whether this blue stuff is a good normalized delta function or something a little deviating. The answer is it is normalized not to 1 but to pi. But we may practice our mathematical curiosity and double check and practice integration of this function, which is the hardest part, although we don't have much time. So I'm going to make screenshots of what we have on the board right now, and then I will erase one of the boards and continue there.
Isn't this n of k the density of the wave vector states?
Well, right now we do not specify the nature of states. It could be like big molecule with a lot of LUMO plus 1, LUMO plus 3, LUMO
What does k label?
Hmm?
What does k?
K labels states, unoccupied states. It doesn't label wave vector. We are not talking about, although it can label anything, right now we are speaking more general.
basically, it takes it.
So we are looking for all occupation of the ground state as function of t, which will be, what do you have up front? Dipole, electric field, some constants, density of state, then we do have the integral of this function. We can call this variable delta triangle, then it will be integral over this triangle, sine square of triangle times t divided by triangle square. Right? Okay, I will go with a shortcut and declare conclusions, and then if you have steam, we will practice complex variable calculus. So I just do not want this boring math to defer us from enjoying conclusions. So integral, well, after taking the integral of our delta function of this function, it will be pi times t squared. So the intensity of this peak grows as square, as you can see from our MATLAB code. And delta function did peak on the value at the delta when you do have a resonance. Then grounds to excited resonance. We do not need omega. Oh, we can. And then if you are looking for the rate, then we take time derivative of this P of t. So how quickly the occupation changes with time. So derivative of 1 is 0, and all constants up front are staying as they were. Density of states times something probably you cannot avoid the let's think what is missing. So we are coming. This will not come to the recording. I will erase it. But we are coming to a paradox. Something is missing in the derivations. There was an error on the way.
Was it when we canceled the second term?
No. The error was at the place where we did select the variable for integration. I think, well, when we meet on coming Tuesday, I will clean things up and make them shiny. But let's just think a little. So most, I guess that the time cannot be removed from integration variable, and if we use t as part of integration, then we need to multiply everything by t squared. So the error is somewhere here, because and then we need to carefully take this integral, and then we will get the right power of this time dependence as function of t. So it is most important part of the whole meeting, and I will need to give it in more details when we meet on Tuesday. So I suggest with this we complete our today's meeting and see you on Tuesday. Change this over. someone wants there are volunteers for each subject. Well, there is only one volunteer for number 3. I will. Meeting is complete. Please feel free to leave if you need to. I'm just trying to.
You email us that. You email
Yes,
us.
I will email it today, so that you have time to think of it during the weekend.